Hello, welcome to XP Actuarial's introductory video series. Today we will be giving you a refresher on some basic financial economics concepts that are important to the exam. The first concept we'll cover today are options. Now we'll define S at T to be the stock price at time T and K to be the strike price. Now a call option gives you the payment of 0 if ST is less than our strike price, but it gives you the payment of ST minus K if our strike price is greater than K. Now a put option gives you the opposite, so it will give you a payment of 0 if ST is greater than K, but it'll give you the payment of K minus ST if ST is less than K. Now the payoff diagram of a call option is the following. If we assume the horizontal axis to be the stock price, we can define the point here to be our strike. Well, the payoff of the call would be 0 up until when the strike price hits K, or stock price hits K, and then it'll increase at a 45-degree angle. The payoff diagram of a put option is the following. It will be 0 on this side of K, and then will increase at a 45-degree angle when the stock price drops below the strike price. The next concept we'll refresh you on is the put-call parity. So suppose we're given the price of a call and the price of a put. It can be shown that the call price minus the put price is equal to S, our stock price, multiplied by e to the negative delta t, where delta is our continuously compounded dividend rate, minus k e to the negative rt, where k is our strike price and r is our continuously compounded risk-free rate. Now t is the time to expiry of these two options over here. To price the options, the exam often uses Black-Scholes, and the price of a call option is s e to the negative delta t n of d1 minus k e to the negative rt n of d2. The price of a put is similar. It is k e to the negative rt n of negative d2 minus s e to the negative delta t n of negative d1. Now d1 is simply ln of s over k plus r minus delta plus 0.5 sigma squared t all over sigma root t. Now d2 is equal to d1 minus sigma root t. Another concept that can be tested on the exam is the delta of an option. Now the delta of the option, if we have the option price C, it is the change in the price of the option over the change in the price of the stock. So the delta of a call is equal to the e to the negative delta t n d1, and delta of a put is equal to e to the negative delta t n of d1 minus 1. Now we do have a handy relation with these two deltas. The delta of a call minus the delta of a put is equal to e to the negative delta t. Now if delta is 0, the stock doesn't pay dividends, and if delta is 0, that means the delta of the call minus the delta of a put is equal to 1. The next concept is the Black-Scholes partial differential equation, and what this states is that the risk-free rate multiplied by the value of our option is equal to Vt, which I'll define below, plus 1/2 sigma squared s squared VSS plus r minus delta s Vs. Now Vt is the change in the value of our option with respect to time. Vs is the change in the value of our option with respect to S, the stock price, and VSS is the second derivative of our value of our derivative with respect to S twice. Now the exam likes to test stochastic stock prices, and the introductory processes that are given in exam MFE are Brownian motions and geometric Brownian motions. Now a Brownian motion has the following process. ds of t, the change in s of t, is equal to alpha dt plus sigma dz. Now this is a normal process. Now the geometric Brownian motion states that ds of t is equal to alpha s dt plus sigma s dz, or z. So the s here is the difference between the two, and this makes this process a log normal process. Now the final concept we'll cover today is Ito's lemma. So suppose we have a stock price or a stock process s of t that is a geometric Brownian motion. We are given c, which is a function of s and is twice differentiable. Ito's lemma states that the process for s of t is the following. So d of cst is equal to cs ds plus 1/2 css ds squared plus ct dt, where cs again is the change in c with respect to s, css is the second partial of c with respect to s twice, and ct is equal to the change in c over the change in time. Now something that's handy for doing Ito type questions is to note that dz squared is equal to dt, and dz dt is equal to 0, and dt squared is also equal to 0. So now we can go through an example. Suppose again we have a process for our stock price, which is a geometric Brownian motion, and we're asked to find the process for s squared. Well, we'll first find cs, which is dc ds. That is equal to 2s. And then we'll find css, which is our second derivative with respect to s, and that is equal to 2. And then ct, which is our derivative with respect to time, is 0. Now we can plug it into the above equation that we solved for Ito's lemma. dcst is equal to cs ds plus 1/2 css ds squared plus ct dt. So we get dc is equal to 2s ds plus 1/2 multiplied by 2 multiplied by ds squared plus 0 dt. So we can simplify this now because we know the process for ds. So dc is equal to 2s multiplied by alpha s dt plus sigma s dz plus this 2.5 will cancel and we get ds squared. Now if we take this whole term, multiply by it again, and multiply it all out, we'll note that dz squared is dt, dz dt is 0, and dt squared is 0. So really all we get from this is this second term squared. So we get sigma squared s squared dz squared. Now we can rearrange the terms here, and we get the following. We will get 2 alpha plus sigma squared s squared dt. Now you'll note that this is equal to dt, so this part comes over to here, plus 2 sigma s squared dz. So the process for s squared is 2 alpha plus sigma squared s squared dt plus 2 sigma s squared dz. This concludes the video on introductory concepts of financial economics.